let's go ahead and try another one on page 123. We're going to try to critique or analyze where this function is increasing, decreasing, and has a possible max or min. So what we're going to try to do first is determine where the critical points are located, and we're going to use those as a basis for us to create that sign chart. So in order to find critical points, we initially have to find the derivative. We can do that real easy now that we have our power rule shortcut. And critical points are locations of possible maxes or mins, and that means our slope or derivative should be 0. So if we set this equation equal to 0, and our goal is to try to solve for x, maybe in this case we can factor to help us solve. So we can pull out a 15x squared out of both terms, and we're left with x squared minus 1. And if we continue to factor using that difference of squares, we'll get x plus 1, x minus 1. So it looks like we have 3 critical points, 0, negative 1, and positive 1. So these are potential max and min locations. We need to create a sign chart in order to determine which one's a max, which one's a min. Maybe it's neither of those. So we're going to take the domain of the original function, and in this case it's just a simple polynomial, like a roller coaster type graph. And that's going to be all real numbers. So we're going to take all real numbers, negative infinity to positive infinity, and break it up in order using these critical points. So that would look like negative infinity to negative 1, negative 1 to 0, 0 to 1, and then 1 to infinity. So if these 3 values are where the derivative is 0, that means somewhere on these intervals the derivative is not 0, implying it's either positive or negative. So we're going to see what case it is. So go ahead and pick any number you want between negative infinity and negative 1, okay, maybe negative 2, and we're going to plug that back into our derivative. Now if you take a look at what we did here, we have the derivative represented in different forms. We have the original, what the power rule gave us, and then we eventually factored it. I think plugging in negative 2 into the original might be a little difficult for us to do because you have this power of 4 and this power of 2. So I think using the factors are going to be a little bit easier for us to figure out, is this positive or is this negative. For instance, if I plug in negative 2 into this x and then square it, I know that this factor is going to result in a positive value. If I plug negative 2 into this factor, that'll be a negative value. And if I plug in negative 2 into this factor, that would also be negative. So if I have a positive times a negative, overall that would be positive. Alright, so we can just think about positive and negatives if we use the factors instead of actually calculating a value if we use the initial derivative. In this case, we'll plug in negative a half. Again, it might be difficult if you use a power of 4 or power of 2, so I suggest using the factors to help you out. A half squared times 15, this will definitely be positive. A half plus 1 will be positive, and then a half minus 1 will be negative. So positive times negative will be negative. If we plug in positive a half, this factor will be positive, this one will be positive, and this one will be negative. So overall, another negative. And for our last interval, if we plug in 2, we'll have positive times positive times positive. So overall we have positive. So using this sign chart, and now that we know what the derivative is doing, we can identify what f of x, okay, this original function would be doing graphically. So positive derivative means it's increasing, negative derivative means f of x is decreasing, and it looks like we go back to increasing. So now that we identified increasing, decreasing, we can also identify maxes or mins. So on f of x, that's where the derivative changes positive to negative or negative to positive. So for this change, we'll have a max, and for this change, we'll have a min. So I think this is a really good scenario if we look at here. Notice how 0 was a critical point. Okay, it was a spot where the derivative is 0. But we cannot classify it as either a max or a min because there's no sign change. So we'll get to what this kind of looks like graphically in a second, but notice how not every critical point is going to be a max or a min. Okay, you have to use a sign chart in order to figure out which one is a max, which one is a min, and which one is neither. Okay, so you always have to check those critical points. So in terms of our justifications, now that our sign chart is complete, we can go ahead and say f of x is increasing on the interval negative infinity, negative 1, and 1 to infinity, because the derivative is positive. Very similarly, we can say f of x is decreasing on the intervals negative 1 to 0 and 0 to 1, because f prime of x is negative. Okay, so we took care of increasing or decreasing. Let's go ahead and find those maxes or mins. So f of x has a max at x equals negative 1 because the derivative equaled 0 and changes positive to negative. They also want us to find the value of the maximum or minimum, so if we were to actually plug in negative 1 into the original function, I believe we would get 2. Alright, so there's an ordered pair on your graph that you know is a max. If we go ahead and write down the minimum, that happened at the x value of positive 1 because the derivative equaled 0 and changes. It'd be wonderful if you could see that. Because the derivative equals 0 and changes negative to positive. Again, if we can find that value, find that actual point on the graph, so if we plug in 1, I believe we'll get negative 2. Okay, so that tackles increasing, decreasing, max, and min, but according to our sign chart, we did have this interesting spot at 0 where something was going on, but we can't really classify it as a max or a min. So if we think about this, notice how before 0 we're decreasing, and after 0 we're also decreasing, but at 0 we need to have a slope that's flat, okay, a horizontal tangent line, okay, because the derivative was 0. So if we think about it graphically, we're decreasing before 0, and then at 0 we need a horizontal tangent line, and then we continue to decrease after 0. So graphically, it looks like a critical point results in a level location if you do not have that sign change required for the max or min. So your graph we can classify as level at the x value of 0. So we'll go ahead and jot that down here. F of x is level at the x value of 0 because the derivative equaled 0 but didn't change sign. Okay, so I'm kind of running out of room here, but I did want to take a second and kind of draw up a visual for this, and I'm going to try to fit it in right here. So based off this sign chart and the ordered pairs that we have, we can start to think about what the graph of this original function would look like. So we said we had a maximum at negative 1, 2, so I'll roughly draw where that would be. And then we said we had a minimum at 1, negative 2, okay, somewhere in there. And then we said we were level at the x location of 0. So if you were to plug in 0 into the original function, maybe we'll go ahead and jot that down here. If you were plugging in 0, you would actually get out 0. So at the origin, okay, we should have that level location. So notice how we're increasing on the first interval, so our graph should be going up. We encounter that maximum or that high point. We continue to decrease after the maximum, but then we start to be level, okay, at the origin, and then we continue to decrease after that until we hit the minimum, and then after that we continue to increase. So there's a rough sketch of what this original function would look like based off the sign chart and our analysis of maxes, mins, and level locations.